till the last day. Hopefully, so far you have enjoyed it, and today you are in for the final treat. We're going to be discussing debugging and profiling tools, and I hope it's going to be very useful for you, and I think it will. The first speaker of today is Sam. You have already heard from him on OpenMP. Today he's going to be discussing our debugger, ROCgdb. Sam, if you want to introduce yourself a little bit, even though they already know you, the stage is yours. Let me unmute you.
Okay, can you hear me now? Okay, sorry, I was talking to myself. Yeah, so I'm Antao. I'm with a GPU data center team as Giacomo, Bob, and others who you've heard from this week. So I do a lot of work around application porting and optimization and helping users making good use of our GPUs. Happen to have responsibilities to the Lumi Center of Excellence. So this big machine with MI250X that is based in Finland. Some of you maybe have played with it before. And yeah, so today wanted to tell you a bit about debugging. Well, I guess I don't know how many of you write code with bugs, or but I'll risk saying that's quite prevalent. So this kind of tools are useful to really help you understanding what's wrong with your code. And I mean, always when I talk about debuggers, I always start saying, that users shouldn't never feel intimidated by using the tools, because I see many more times than not, a lot of work going into trying to find a problem that a debugger could, much easily pinpoint, the origin of your problem and get into the solution track much quicker. So today it's about the AMD debugger, the ROCgdb, so the debugger for our GPUs. So let me see if I can switch slides. Yes, I can do. Okay, so what is ROCgdb? So ROCgdb is a source level debugger. So this is based on the GNU debugger. So this is possibly the most widely used debugger, and in many ways it follows the developments that happen on GDB, right? So the experiences that you have with using GDB for your CPU code, you could just leverage a lot of that for debugging your GPU code as well. So the ROCgdb is kind of considered a prototype in the sense that it's not completely, feature complete in comparing to its CPU counterpart, right? It mostly focuses on source line debugging, so it doesn't have like this dwarf information. It's still limited to tell you, to allow you to navigate, say, complex data structures on a GPU and things of that sort. So this stuff is not kind of supported on a GPU. So in this sense, you can consider this as a prototype. Because it's based on GDB, a lot of the tools that work around GDB also work with ROCgdb, like connecting remotely to the debug session, the GUIs. So a lot of things you can leverage for GDB, you can also leverage for ROCgdb. So just I'll just leave in here the link for the exercises. So that's what you'll be doing after this talk. I will see it'll be kind of a very simple application, but the goal of this exercise is not really, the complexity of the application is really give you an opportunity to experiment with ROCgdb based on a SAXP kernel, which is kind of the example that will be kind of showing here in this presentation. So it's kind of a step-by-step experiment on using ROCgdb and what you can expect, if you are using this kind of tool. So this code here is SAXP code. You see here in this area, you have the kernel, a SAXP kernel. So this is the part that is going to execute on a GPU. And here on the bottom, you have the CPU part, consists of some data allocations, and then the issuing of the kernel, the SAXP kernel to the GPU, followed by a synchronization. A few things that I wanted to pinpoint here because it's kind of important when you use a debugger is to understand, what is your dispatch configuration for this kernel. And in this case, we have two groups of threads, two work groups, and each group will have 128 threads. And my problem size is 256. So if I multiply, so basically this, this configuration allow me to cover, all this problem size that I'm interested in covering here in my GPU kernel. So how does this is actually executed on a GPU? It's pretty much like the picture you have here on the bottom. You have two groups. Each one will be running two wavefronts. So as you may remember from what I discussed this week and before, so the execution is partitioned by waves that execute in lockstep. So we have these wavefronts split into two groups. And this is kind of important in the sense that the debugger will kind of logically split the information for all these elements that we have here. Okay. So, just a bit more explanation here. So this part here is the part of the kernel that is going to control the indexing of our arrays. So basically, the ranges that are going to be referenced from the pointers X and Y, and E just going to insert kind of a problem or an error or bug in our code by commenting out the two lines that allocate the data. So basically, this is going to make all the accesses to this, pointers that are uninitialized, wrong, and is going to cause a bit of the problem. One thing that I wanted to stress here. When you offload to the GPU, this is kind of done asynchronously, so that you just offload some work for the GPU, and you only know if something actually went wrong when you try to synchronize with it or try to do some activity, after the failure happened. Right, so it's important that if you are debugging a kernel, just make sure you synchronize after it, so you can catch all the exceptions and problems that may have arisen from the kernel. So this is why the synchronization is here. So it's always very important to do that, because it's very common sometimes you issue many kernels asynchronously, and then you have a synchronization and you just see an error and you just assume that has to do with the previous one. So when you are synchronizing, after a lot of asynchronous work on a GPU, then it's a bit more confusing to pinpoint where things are coming from. Okay, so next thing I'm going to do is to compile to our target GPU. So these are the different targets. You have your own MI200 machines, also have the AC MI300, so you could tune your compiled based on this flag. So you can even code for multiple different targets. We executed, and boom. So we have our problem. And usually, when you get this access fault on a GPUs, that this is kind of the message that you see on your command line. So memory access fault on a given GPU. There's a handle. There's also sometimes it can be more or less useful to the address that caused the fault. And reason unknown is like, there's no clue whatsoever what resulted in this new pointer here being accessed, right? So this is you have this sort of message once you try to execute it. So with this, we have a good target for us to try to debug and find what the problem is in our code. And this is kind of a cheat sheet of the GPU, the GDB command, right? So and this, if you have debugging to the GPU with GDB, a lot of this here should look very familiar. I'm not going to go exhaustively over this list, but there is the part that is important to start your program, and then to run, to basically have the threads progress on the different pieces of your code, and then the part that controls the breakpoints and also the dumping of the information about the variables, the listing of them, and also navigating on the stack, right? So if something breaks on a very low, on very deep in your stack, you may want to go up your stack and see where that call chain generated from. Okay, so let's execute this program with ROCgdb, and this is how you to do, like, exact same thing as you would do with GDB. Just a reminder that in many cases, not the case of this example, you may have arguments that are passed to the application, and if you just do ROCgdb --args, those arguments will be will be captured to be executed within the debug without you having to specify them again. So it's usually more convenient than just doing this into separate steps. When you do after starting your debugger, you see this program, this kind of terminal, and you issue a run command to start the execution, and this is what you see. What message you see coming out of the debugger. This is a segmentation fault because of the invalid access on a GPU, and will also tell you where the problem happened. So which kernel caused the issue. In this case is the XP kernel, as you would expect. Now, another thing that is quite important when we are debugging is to make sure that we build your code with debug symbols. And this is what we recommend doing. I think -g just works most of the time, but you can use -g just to target a bit more the debug information to GDB, because that's what we'll be using for debugging for the GPU. So this is what we recommend. And if you had this bit to your build command, then this information about your source code is going to be captured within your executable, which will allow you to have a bit more information about the lines where the code failed. In this case, as expected, is in this line where the pointers are being dereferenced. Okay, so the other interesting thing about ROCgdb, and that's the thing that starts to be a bit more, different than your, say, CPU normal experience of debugging for the CPU, is that you have a different set of threads. So there is the threads that actually execute on a CPU, and these were the threads that will be calling the ROCm runtime and do whatever work your application needs to do. But then there will be also the threads that are executing on the GPU, and they show like this with AMD GPU wave. And you have as many threads as waves, right? So as you remember, all these waves are executed in lockstep, and it ends up being a bit the logical unit for which you debug things, because all the these threads in this wave execute in lockstep, and so in a way here you are feeling a bit of what actually happens physically on a GPU. You have a SIMD unit executing a lot of things in parallel, so that's why you have each SIMD unit executing its own thread. That's how it shows in waves on ROCgdb. So with this command eth, we list all the threads, so we know there is a bunch of CPU threads and a bunch of GPU threads. Right. So looking a bit more on a CPU thread, you see, and actually, I'll just warn you that out of the box, if you just build your code against ROCm runtime, you won't have debug symbols there, so you won't be able to see this. So actually, what I'm showing you here is obtained with ROCm runtime that has been compiled with debug symbols. So I mean, there is ways to do this. It's open source, so you can go and take a look at the code, and you can also build the code and get debug symbols. So this is what we are doing here. That's why you have a bit more verbose, more information here on the stack. Otherwise, you just see maybe an interrogation mark. But about the CPU thread, this is usually where it stops working, right? So when it's on runtime call, waiting for something to happen. on a CPU. You can decide to list all your stack, and usually it looks a bit like this. So you have the lower level, what you call this HSA runtime, which is a lower level runtime, and they have the heap runtime. So the heap runtime is implemented on top of the HSA runtime, and then on the very top you have your application. And well, no surprise that the problem happens where we are synchronizing, so waiting for the work to finish on our GPU. Okay, so just a quick tip. Well, a lot of applications use many threads, right? So and some frameworks. I mean, OpenMP, even Python. If you use Python, you'll see that will be many threads on flight. And so if you are debugging something, your debug, be a bit cluttered by all these threads. So it's usually a good idea, if it doesn't make a difference in the failure that you are investigating, to use as few threads as possible, and even better if you can just do this in one thread. With OpenMP, which it can be done by setting these OMP num threads variable, and with this you could just have the thread is actually doing the work on a CPU, which is much easier to analyze and understand. And another thing is when you use MPI, you cannot hook up GDB to MPI itself. You need to hook up GDB to the individual processor that MPI spins. So it's something to bear in mind. So if you want to do debug about MPI, you may want to use a proxy script where that calls ROCgdb, for your application, for a specific run. So this is a common way to go about debugging with MPI. Okay, right. So the other thing that you might be interested in doing when debugging is just to use breakpoints, and this is how you would do that. You just do B and the name of the file and the line. You may also choose to breakpoint at specific functions. So in this case, and that's kind of a common pitfall that if you specify a command line and sometimes the breakpoint doesn't show up exactly on that line, because it's dependent on how your code was generated, right? So like in this case, we have line number 22, and well, it's it would or not be a bit surprising that the breakpoint ends up being on line 1 to 8. And the reason for this is optimization, right? So when you compile your code, the compiler optimizes the code, which means that a lot of things may actually not be executed in exact order that you see here. So it's not uncommon to see this sort of behavior. Yeah. So what should we do to tackle this? And again, if it doesn't make a difference for the issue you are trying to identify, try to compile the code without optimization. Of course, keep your GGDB just to generate a bug symbol, but you can add this -0 just to disable optimizations. And in that, if you do that, the compiler will generate the code exactly as kind of shown in your source, and this makes it much easier for you to navigate your application while debugging it. So if you do this, then the breakpoint actually shows at the correct place. Okay, so more interesting things you can do. So here, well, there's shortcuts. If you use GDB, you'll know that you can write run, or you can write just R. So you could that breakpoints or B to breakpoints. So you can of course just have very simple keystrokes to start your process and navigating it. So in this case, we just set a breakpoint on our main. Right, so when you run, we just the thread just stops there. And one thing you can try doing, well, at this point on code, I have this thread, so let me query what actually architecture these threads relate to. So when I'm eating my main, function. Of course, everything will be still on a CPU. I didn't get to the point where I actually offloaded to the GPU, so all the threads are expectedly CPU threads, and that shows like this as x86/64 architecture. If you ask for the architecture, this is for the CPU. If you do a similar thing to the GPU, so instead of breaking point on main, you just break point on the kernel. You can just do wait for it to actually hit the breakpoint. So this like continue the execution for your SAXP kernel. And if you query what is the current architecture associated with this thread where the breakpoint happened, it will show you, in this case, is MI200 series GPU, GFX 908, or you could see GFX for 942 for MI300A. Other things that you might be interested in exploring, again, ROCgdb leveraged the GDB framework. So a lot of the tools, particular GUIs that you have that work with GDB should work with ROCgdb. I mean, one that I actually tend to use quite a lot is what already comes with GDB. So you can enable like bypassing this -2 option, or you can just after running enable TUI, and it will show you your source code and highlighting the line where you are, and you have the normal console on the bottom that you can use the commands we just discussed before. The other tools like CGDB, you could just explore away and try to use with your favorite interface to GDB. This is like an example with ROCgdb and GDB GUI as well. So pretty much all offer similar experience, just a matter of taste, I guess. Okay. Okay. So right. So this one of the important aspects of when you debug your code is that you could also choose to go look more into the specifics of the architecture and how things are executed. I already hinted a bit on that by talking about the waves. So this picture here is kind of just a recap of the compute unit architecture. So you have the CMD units, you have 4 of them. So each one have 16 waves. So because you have 4, so you have these 64 waves. You have a local data store 64K. You also have 64K of registers. And one of the good news about this is this picture here actually doesn't, logically doesn't change much if you go to MI300A. So in terms of the CU and how the abstraction of how the compute unit works is pretty much the same between GFX 90 whatever, MI210, MI250, or GFS 942, which MI300. So it's pretty much this is the kind of the same the same thing. As I said, so these units here then own kind of a wave executing in 4 threads, and you can execute up to 10 threads, right? So you can imagine that a CU can execute up to 10 threads with a vector length of 64 lanes, which means that each thread can use up to 256 vector registers, right? This is how you can think about this. And this information translates a bit to what you see out of your debugger, in particular when you start parsing the information about threads and waves here. So just so how do you get this? So ITH or info threads, you could list all the threads, and for the GPU threads, it has these numbers here. And how you should interpret this is basically as shown here. So the first part you see here has to do with the ID, so of the GPU. We call it agent ID. So in a node, all AMD devices have an ID. GPUs and CPUs. For the GPUs, there's a given ID that shows up here. So if you use different GPUs on your application, you should see different IDs shown up here. Next bit here has to do with the queue ID. So the GPU supports concurrent dispatching. So you have multiple queues you can use to schedule work in parallel. So there's like a limited number of queues, but there are several, and they use an ID. So with this, you can understand which queue was used to dispatch your kernel. The next information here is the dispatch number, and this has to do with say the index of the activity that went through that queue. Say if you execute this XP multiple times, so its first instance will be 1. If the second instance goes through the same queue, then it will be 2. So it can tell you a bit the instance, what is the instance of a given kernel that was executed. So, and it kind of increases with all the activity that grows through a queue. The last one is the wave ID. If you remember from our application, we had 2 groups with each with 128 threads. So we have 4 wavefronts. So this is the 4 wavefronts that you see here that map in GDB to 4 threads, as we were discussing in the architecture slide I was showing you before. The other information here is kind of the logical partition on these waves, right? So this I'll say this part is more about the hardware. This part is about more the work group wave abstraction. So it shows you what is the logical partition that you selected for the execution of this kernel. So you have work group 0 and work group 1, and each one will have a different ID, and you have ID 0 and 1 for each one of the work groups. So this is how you can interpret this, and this can actually be very important information, because sometimes you can just, by doing some simple math, you can understand based on the IDs of the waves and work groups, what is the offset you are referencing from a pointer, and see if you make sense. Sometimes just by looking at this, you could make a lot of progress in your debugging. Okay, there are a few more advanced things you can do, like inspecting, changing registers, changing memory, change LDS. You can go through assembly instructions one by one. You could even try getting to sorting race conditions by progressing different waves independent on a GPU. So this is quite more advanced things that you might be interested in doing. Other things you can also know from GDB is querying information about these different hardware entities that I just mentioned before, like the agent. So information about the agent. So each agent is ID1. All right, you can say ID1 is this specific GPU, has its architecture, has many cores, there's many threads. And again, threads is like what a SIMD unit is doing. You can query about the queues, right? So in this case, it tell you what queues have been used and how many actually packets. So AQL stands for is like a standard that is used for the runtime to communicate with the GPU controller. So these AQL packets, and it tells you the packets that were sent to each queue, or the sizes, the corresponding sizes. So this is kind of very low level information, and also the dispatch, right? So say, oh, what is the this specific dispatch with the instance of the kernel, or that I'm doing, or a specific instance of an activity I do on a GPU. And this is how you could also query info dispatches. Is show what a dispatch refers to. In this case, I'll only have kind of one for the SAXP kernel. Another thing that you might be interested in doing is to complement your debugging activities with ROCgdb with this environment for eyeball that you can set AMD log level equal 3 or equal 4, and it will show you, it will give you a trace of the runtime activity that is going on you know, in your code. So you run this kind of goes in your screen. You can have a GDB instance running, and you can, for instance, try to, you know, in this case we have a kernel here, you know, that is launched here with a few arguments, with some pointers, with this estimated range here, and you can try to detect these pointers on a GPU, see if it makes sense. So you can, you know, in a way complement, you know, your debugging experience with GDB with this tracing that you can get out of AMD log level. So it's something that you know, might be useful for you to explore. And you know, this is like some slides that we have here just as a reference. You know, so we have come across people that really want to use GUIs, you know, and on your local machine, and you want to hook it up with something going remote on your server. So there's like, you know, different ways to, well, not different ways, but like a bit of a instruction on how to do that. I'll give this here as a reference. You'll have the slides after this this presentation. Yeah, so basically tunneling to, you know, connecting to a node and run your GDB GUI locally. You know, this is some things you can decide to explore. Just to close here, you know, there are several resources that you could explore for ROCgdb. You can start with what comes with the ROCm installation. Of course, this also is available online, and there are like a few other resources that you can find. I mean, well, I will say virtually, you know, the way you interact with GDB is pretty stable. It's been pretty stable. So even presentations that, you know, maybe have a few years old, they are still pretty much current. You know, the GPU architecture, how you do, you know, queues, agents, waves. You know, this has always been pretty much the same. So this videos and presentations you can find online, you know, are still pretty much current. You can still learn a lot from them. So just to leave them there in the slide. And with that, you know, this is the end of this presentation, and I'll encourage you to go try the exercises. So actually they were listed in the link is exactly, the link is this one here. You know, if you want to go to that link and explore that, as I said, you know, the goal of this exercise is pretty much kind of open-ended, in a sense that, you know, it's a very simple application. Is more for you to, you know, create the segmentation fold, use the ROCgdb to understand what happens, see the threads, see the waves, see all this different information I showed you, and yeah, just get a bit more acquainted. And as I said at the beginning, you know, don't be intimidated by debuggers, and you know, it's really important tools that you should get on our toolbox, and can save you a lot of time if you have a, you know, more complex piece of code to debug. So thank you very much for your attention.
Thank you, Sam. That was a great talk. Okay, so for the schedule, now we have time for exercises, just as Sam said. And then there's gonna be a break at 2 p.m. Edinburgh time. And the next talk will be at 2:15 by George and Luca, ROCprof and Omnitrace. So as usual, we'll be available in the Mattermost chat to answer any questions, and we'll be on for a while here, at least until the break, just in case anyone wants to ask anything live.
Yeah, very good. I'll monitor the chat. You know, let me know any questions. I'll be around next half an hour or so. So maybe I'll just use this opportunity just to say something that I wanted to say earlier, but I guess it's more targeted at sysadmins, about the debugger. In a sense, this tends to be a bit of the component that is a bit more sensitive to the driver levels you use. So we, in a way, we have some flexibility in mismatching a bit the user level ROCm with the driver level. But the debugger tends to be a bit more sensitive to this. It requires specific driver levels to be able to really get information of what's going on a GPU. So just another bit of information for for you to have on the back of your heads.
Okay, hello everybody. My name is Markomanolis. I'm in the same team with everybody. I would say working a lot with RFPs is about the procurements and some applications supporting users, trainings and hackathons. And I'm based in France, so we're a few people in Europe. Well, they're not only all the team in US, and we have a lot of the European customers. And here today we'll present basically it's a few presentations merged, me and Luca. And I will start with the ROCprof in 3 minutes as I see the time.
Thanks, George. Yeah, and Luca, if you want to chime in as well, you have already introduced yourself on the first day, but maybe it's good to do it again today.
Yes, it seems like I'm doing a little bit of recap today because I'll also be doing a little bit of recap on the Omnitrace presentation that was already presented yesterday by Gina, but also some other parts that were not presented yesterday as well. So my name is Luca Stanisic, and I recently joined AMD, also working in the same teams as others that presented this week. And I'm also actually based in Europe, in Munich, and I work closely with Max Planck Computing and Data Facility. Yeah, so today with George, we're going to present a couple of different GPU timeline profiling tools, and I hope this will be useful for you.
Thanks, Luca. Yeah, we're scattered all over the, well, I would like to say the globe, but it's mostly North America and Europe. I'm in Austin, Gina is in Houston, Bob is in Los Alamos, Luca and Sam and John in Germany, and George in France. Ian is in the East Coast. So we have some kind of 24-hour support happening here.
Okay, I think we can start. So in this slot, we're going to present some profiling tools and let's see about timeline, not exactly inside the kernel, but what happens to the timeline of applications. And this is first time I think we'll present this exactly. Is about the ROCprof v3. And what's v3? And I don't know if you know the ROCprof in general. Probably you know if you have played a bit with the AMD GPUs. We have like 3 versions, but they're not all active, all the same important. So we started with the ROCprof. It was integrated in the ROCm for a few years now. It's open source and contains several components allowing application traces and counter collection. And it's under constant development, but slowly we decided that the ROCprof had some design that it was not what we wanted to use as efficiency, as working API, working with other tools. So there was a version 2, which basically combines some ROC traces and ROC profiler into a single library, same API. But the team who works with the profiling tools developed the ROC Profiler SDK, which is a profiling and tracing library for HIP and ROCm applications in general. And the new API improves thread safety and includes more efficient implementation. And something really important is about the callbacks to work with external tools. So that's why the ROCprof version 3 use this tool library to profile and trace applications, but also AMD collaborates with other external tools also that they can use this API and instrument code. So technically, the V2 is not really used now. If you have less than ROCm 6.2, you use ROCprof v1, which is called ROCprof. And if you have 6.2, better use ROCprof v3, that is the name of the executable. Really generic, and because maybe you have seen from other presentations, we had the ROCprof initially, okay, that does a ROC collection of GPU counters and traces, counter collection with user inputs, provides CSV files. We'll see now a different trace on v3, trace collection support for CPU copy, heap API, HSA, and GPU kernels. And traces are visualized with Perfetto. I think probably you saw already something, and you can load them on Excel. And then you have the Omnitrace that I will not say a lot because Luca is talking next to it. Basically, Omnitrace combines GPU and CPU and more layers. I would say it's like the Swiss Army knife compared to ROCprof, but ROCprof is more, you can start directly, while Omnitrace you need to do some extra things that Luca will say, and Omniperf later from Ian. So Omnitrace, you see the timeline, but you don't know, is the kernel efficient? And then you use Omniperf with a lot of metrics, and I will stop here because you have later more information. But I want to say that there are many various tools, and like how you use them, what you use them, and what, for example, there are some objectives, right? Where to focus my time, like timelines, traces, profiles, or how well I'm using the GPU. Also timeline, but also roofline, and why I'm seeing bad performance or good performance hardware counters. And before, all of them will go into ROCprof. So the teams decided that this is too much work, and let's have different tools to use based on a different objective, right? Omnitrace for timeline, Omniperf for kernels, and many of them, they will use also the API that ROCprof v3 use to do the instrumentation, etc. And I want to mention really generic about ROCprof v3 now. Okay, it has some new arguments compared to ROCprof. Some are similar, some are new, that you can collect, for example, heap traces, runtime plus compiler with this one, or separate them based on these arguments. The ROCtx now is called market trace, and you can do memory copy trace, so to see from device to host, see how many bytes, etc. And this is all tracing. And if you add the stats, does statistics also per command, per kernel, etc. And this is the HSA. I suppose, I'm not sure if you know what this HSA is about. The heap doesn't talk directly to GPU. Heap talks to HSA, and HSA decides what to do on the GPU, etc. So it's another layer below heap. And the options continue. And I want to say the DAS-T is truncate kernels, which I suppose you understand. If you have kernels without same name, you can use that to remove all the arguments. That takes a lot, maybe line in the output or a lot of data. But if you have the same kernels with different arguments, you need to not use that to have all the separate which kernel is whom if you depend on data type. And you can do kernel trace, and you can do various stuff, preload stuff. And the other difference is that with ROCprof v3, you activate heap trace, for example, and then you have das, my application, and your arguments. So this is also new compared to ROCprof. And there's a nice instructions on here on this one web page, and you can see a lot of information about the tool. Again, on container, you have 6.2.1, so you can use this tool. But I mean, not every system has 6.2, so you need to be aware of it. So for kernel information, for example, this is a Giacomo example, and say I want statistics about kernel trace and activate the DAS-T. So this will create some files. So basically, this is like one process, right? This is not MPI run, it's just basic. And the XXX is some numbers, okay, from process ID, etc. And there will be one file, agent info, is information about the used hardware, APU, GPU, and CPU. And then the kernel trace is information per each call of the kernel, okay? Per each call of the kernel, you have some information, and I have here a small output of the statistics. This is statistics. So imagine here this kernel is called 1,000 times. Here's the number of the calls. On this file, you have 1,000 lines of this kernel, not continuous, but when it's called, is printed in the trace. And statistics, this is statistics of this example. And the domain statistics is basically categories of what domain is that. It's the commands. Is it kernel dispatch? Is heap compiler API? Okay, this is more generic. And and the output of statistic kernel is this one, which if I load it or use a spreadsheet, you can see this one to understand better here. So number of cores, total duration, average, percentage. The percentage is a good metric to know 53% of my time is this kernel. So I don't know, doesn't mean it's good or bad, but no need to go to work for something that's 0.4%, right? To improve the performance of something. So it's a good first feeling to say, maybe I should try to see if these top 3 kernels, for example, are efficient or not, okay? And you have the minimum and maximum duration, standard deviation to see the variation, and if you expect that this kernel should behave the same or not. And then if it should be the same, you can go to the timeline to see the difference in how they behave. Now, a bit about collecting application traces. So the heap API call is a heap trace. GPU kernels, you do the kernel trace. So this one with the heap, this is the kernel trace also. Host device memory copies. The heap trace does the heap mem copy, but this one will tell you information also about the moved bytes and other stuff. It's also nice. HSA, not all the people do HSA trace. The ROCtx again, and this one, the systrace, does everything. Heap, HSA, kernels, memory copy, marker API, if there exists ROCtx, instruments everything. So this is also nice. And the scratch memory trace is something new. This one is, I don't know if you're aware about the local memory that's like private to each thread, like I want to do register spilling or ROCR runtime allocation, etc. You can see there what happens in this memory to see the allocations and deallocations, etc. And of course, you can combine this, right? You can do stats, heap trace, HSA trace, and here I say the new format, PF trace. The ROCprof version 1 had JSON, and with Perfetto and JSON have seen many issues, and the PF trace seems quite more stable, and I will show you about that. Now, collecting and visualizing applications, so I do like heap trace and PF trace of an application, and then I go to this website, and I say, please open trace file, and I load the PF trace. Of course, I have downloaded the file to my laptop to load it, right? No, I don't do it from the machine or the remote machine. And then you start seeing here, one moment to go like that, the heap API activity, okay? This is the main thread, and you can see the GPU activity, and you see the queue that also is used, and the GPU activity is here, and the copy activity. So see here, I see copy and to CPU and GPU also. So it's quite interesting to see. Of course, this is really generic view. This is really high level. And I forgot to say that the x-axis is the time. So as you go on the right, the time goes on. And in the real web page, you see also the time here on top for it. Now, I had a question also, what is this thread? This can disappear in the next ROCprof. The told me it's like an extra thread on CPU that does some heap HSA interference calls, but it's something that the profiling team created and maybe will remove later. So it's not something from your application. No need to worry about it. You need to focus on the actual stuff here. And here is like a zoom. This is before, and I go to zoom inside. How you zoom? You see here W zoom, S zoom out, A move left, D move right. The keyboard, if you have the proper keyboard, at least you can move easily. And you can also see the kernel, okay, the heap launch kernels, for example, and here's the HSA layer. In this case, I use the systrace to instrument everything. And when you go to the kernel and you click, you can see the flow of events, which flow called this one, okay? So it's quite easy to understand and see what's going on. And also, if you go here, he said here, and you click, you can start open this. I have selected one moment. I have selected this kernel. Okay, this kernel is here's the black. I have selected, and I go here, and I go inside, and I see the duration, the kernel name with the options, and the workgroup size that I use, and the grid size. This is really nice because sometimes you say, I'm not sure if this kernel uses a correct workgroup size. The 256, I suppose. Now you know what it does mean compared to wavefront and other stuff. So there is a lot of information that you can see from here, from a kernel, from the Perfetto with the PF trace. Just to mention, the JSON and Perfetto is a long story. I would say personally, don't use JSON files. Go to PF trace or ROCprof 3, and it's quite stable. And also the ROCprof, the new one, does also some support to see some OpenAPI offloading. So the option kernel trace provides information. You can use also HSA trace if you want, but for example, I did like that statistics kernel trace, okay, and had only it's a group. This is statistics, so it's only one OpenAPI offloading, and the number of the calls and total durations and etc. And the other, not statistics but tracing. For each call, tell you information for each call of this, of OpenAPI offloading. So before, to my knowledge, you couldn't see that, but this is really nice to see it with a ROCprof v3, so to see new functionalities, etc. And also, you can visualize also, right? And you see here the OpenAPI offloading stuff, who call it, information of the workgroup size again. And this one, I think, I did it with systrace output format, but you can call also kernel trace output format PF trace. It's not so difficult. I would say ROCprof is really fast to start and see what happens, what I want to focus, and what seems suspicious, I would say. Now, ROCtx markers, that was a bit more good for me for the ROCprof v3, because if you are familiar with ROCprof, there's a new changes. You have to include a new header here, because this was before it was ROCtx, but now you have to define the SDK ROCtx, and also to link ROCprofiler SDK ROCtx. Before it was different library. So if you don't do that, you will see nothing on the trace, and you will think that something is wrong, because ROCprof v3 changed this aspect. I'm not sure if we'll change it back to the default, but the team knows the difference, and will decide what to do with that. So what is that ROCtx? I don't know if you know already. It's like I have simple words. I have a region of code, and I want to give a name for it to see the trace. Now this is not the actual, this is another code. So for example, if this is called reduce for C, you will see here reduce for C, okay? You will see something here of this name. This code is from the Ghost Exchange example that we have in the repository, and has ROCtx, and you can see regions of code. So you can go to lines, give you a random example, 5 to 10, and say call them boundary update, because this is what the lines does, okay? So it's really nice to see specific lines of code, how they perform, etc. And merge traces. So I did again Ghost Exchange. I had 4 traces. I said cut of them in redirect them to one PF trace, and then visualize all of this. And you can see the 4 different. All of this is one API process. Okay, not just API, but the process of the call. 4 API process, and you see them in the timeline. For example, this should be similar. This line sounds similar, right? So something's delayed here, so you can investigate like that between processes, what push, write something else, and try to understand how to fix it, etc. So also this one was not working with JSON, and also with PF trace is working, and that's quite good. And the GPU counters, I will not talk a lot because I think the time goes really fast. You can see, for example, many stuff about the VLU utilization. It's nice to have counters that the value means something, right? For example, CU occupancy, the ratio of active waves on the compute units to the maximum number of the active waves. It's something to see about how much I utilize the GPU. Doesn't mean that it's efficient, but to see if my problem size is small, I can't expect to go close to the peak. And you have a lot of here counters to see here in the repository. And again, how you use the counters, you create the text. You can see first of all the counters from here, -L, and you see all the counters. It's really nice. And you create a TXT file with something like that. Depends on the counters. You do PMC and some counters and another counters. Each line means different execution of the application. So this one will do 2 executions, and I do -I, the TXT file that has this one, and run the application. Okay, and so this will create 2 directories in this example, PMC1, PMC2. Okay, for the 2 lines in the file, and you have here files to see what's going on, CSV files to see for each call the counter that is. This is per MPI process, and of course you can create also trace if you want, etc. So there are plenty of stuff you can do on ROCprof v3. And yes, the profiling overhead, really simple. If you try to profile like a ROCtx in a loop, this is a lot of overhead. So you have to be careful to compare before and after. If something's like 50% overhead, you should not compare so much the results, because you have to identify why this overhead first. And ROCprof v3 has less overhead than ROCprof v1 for various examples I've seen, and extensive with codes with extensive ROCm calls, and that's quite good to know. So ROCprof is open source. It's at ROCm 6.2. Provides tracing for GPU kernels. It can use GPU hardware, of course. Perfecto seems to visualize PF traces files without issues. I mean, personally, I didn't see an issue, so I would say avoid the JSON. And there are output files like text CSV format. You can use them and grep data and do your own stuff and visualize. And with that, I was going a bit fast because we have more slides, and Luca can continue. Can you take the control?
Yes, I think I can take the control, but I first need to unmute myself, and then should be okay now. Yep, seems to be okay. Thanks, George. So George today presented quite some things about the ROCprof, actually ROCprof v3, so the latest version. And you have seen that there are a lot of things that you can already do with it. On top of the ROCprof, what we have and what I want to present today is Omnitrace. Omnitrace, you can see it kind of as a tool for a holistic view, not only of the GPU, but also CPU and the whole system. So it gets information, a lot of useful information from ROCprof, but also gets a lot of other useful information from useful things like perf, like MPI things, PTED. It can provide profiles, things from ROCm SMI, and so on. Just like you saw already yesterday, Omnitrace can also be visualized with Perfetto. So Omnitrace is an application profiling, tracing, and analysis tool. It can collect, as you see below, different CPU and GPU metrics. Also, there is support for different types of parallelism and languages, as well as different type of data collection modes and analysis modes, which I will talk a bit later, a bit more. And the new features are constantly being added to the Omnitrace. Perhaps the most interesting and the latest information, especially for those of you who already know a little bit about Omnitrace from before, is that the Omnitrace was recently added and became really a part of the ROCm software stack. So it formerly used to be an AMD research tool, but starting from ROCm 6.2, it's really part of ROCm, which is actually quite good because it suggests AMD's plans for long-term support and better support for this tool. let me now go through several elements, some of which were presented also yesterday regarding Omnitrace, but here perhaps going into a few more details and showing a few more other things. So first thing that you do when you get Omnitrace, when you start on a new machine, is of course you want to check what are all the data collection capabilities, what are all the hardware counters, what are all the things that you can actually profile with Omnitrace. And to do that, you use Omnitrace-avail. And then there are several different options, so you can check different categories. You can perhaps select one category, for example, here, ROCm, and then you will see all the environment variables for ROCm below. Or you can select an Omnitrace, then see different things for Omnitrace, and so on. Another useful option is -bd, with which you can get a description for each one of these variables, which can be useful because for some of them you might not know what do they represent. Then when you're finished with that, you can create a config file and here select all the, this is the content of the config file, and here select with false and true all the things that you want to enable or disable. Note that some of the features of Omnitrace are considered advanced. So when you create this config file, they will not appear here in the file. However, you can find them if you go through the help and append them here to this file. So then the next step typically is to do a binary rewrite. So basically, by using Omnitrace instrument, you want to create an instrumented binary of your existing application. So in this case, we're using a Jacobi HIP example from the HPC examples repository. And then basically here, what you will do is you will select what kind of output you want. And here, again, -- and the actual application that you want to use. Of course, Omnitrace has a lot of different options, and you should check some of them. So for example, by default, the instrumentation will only be done for the main function and functions that have more than 1024 instructions, but you can, of course, change that or select the function names and so on. When you run Omnitrace here, you will get this type of output. And perhaps the most useful thing are these in green, these paths to the files, especially the text files, which will show you what are the available functions for instrumentation, what were the ones that were actually instrumented, the ones excluded, and the ones overlapped. When you have the instrumented binary, then you just do, you run your instrumented binary. So for example, here with MPI run, you do Omnitrace run -- and then note that here I'm using the newly created binary. So here you will get the output first. You will get some ASCII art for the Omnitrace, some initializations. Then you will have the output of your application here, and then below you have some things for the finalization. And actually, perhaps the most useful thing here in the output at the very end again will be path to all the output files generated by the Omnitrace. So what I typically do is I just select them there and then copy the path in my terminal in order to open the text files that I want to inspect, rather than searching for them in the terminal, doing autocomplete, which can be error prone. So as I said, one of the perhaps the most useful things, I believe, here, if you enable this Omnitrace profile option, is to get this vault log file. So basically here you'll have a list of all the functions that were traced, and with some statistics of how many times it was called and how much time it took, and so on. If you want to see a bit more aggregated view, which is often the case, you can use this additional on top of the profile. You can add additional option, which is Omnitrace flat profile tool. And you can either add that to the Omnitrace config file, or you can also use it when you are running with MPI, just to prepend your MPI run, which I think is quite useful sometimes when you want to test certain options but not use them all the time. And in this case, you will get here this aggregated view with all the things, again, with the count and sum of all durations, mean, and so on. So very often this vault lock is, I think, sufficient to get the overview, but sometimes you want to go a step further and visualize the trace. In this case, you will use Perfetto. I think I will not go too much into detail with Perfetto, as it was already presented a little bit by George today and yesterday by Gina. But basically, you copy the trace to your laptop, you open in the Chrome browser, open the trace, and you get a view something like this. So here, this is a classical Gantt chart with the timeline on x-axis and the resources of different metrics on the y-axis. And here you can see the traces of, for example, CPU functions. Here on the left, the CPU matrix, and so on. You can navigate Perfetto with the WASD on your keyboard, and also zoom in. For example, here we zoomed in into one part of the execution to see better what are all the kernels there. And then finally, you can see additional things in Perfetto, such as the flow of the events, such as you can select the matrix of interest that you want to view together, so you can pin some of them, and also GPU characteristics. So note that sometimes Perfetto it provides you really a lot of different options. So you will have quite a lot of things on the y-axis to scroll. So very often you want to pin the ones that you're mostly interested in, just to be able to compare different rows. So now let me talk a little bit more about something which is also available in Omnitrace in principle. So from ROCprof, what we are getting is also different hardware counters. And here there is a list of all of them. I mean, there is quite a long list here. There's just different snippets of different parts. But the main point of this slide is just to show that there are really a lot of different things. So there are CPU hardware counters from PAPI and Perf. There are GPU hardware counters, environment variables, components, and so on. So really check for ones that you're mostly interested in, and select the ones that can give you the most information about your application. So the way to use it is that you configure your Omnitrace, either your Omnitrace config file, or as I said, prepend your MPI run, and you basically add here a list of counters that you want to check. So for example, here you can even select on which GPU you want this to be measured here on GPU 0, but you can also use of course for all of them. One thing to note here is that actually we are currently experiencing some issues with ROCm 6.2.1 regarding these counters, in a sense that counters seem to be quite well captured by ROCprof, but the information is not propagated well in the Omnitrace. So actually, if you use Omnitrace to collect counters in the training containers with the latest ones, you will actually get the output files, but they will be empty, which is clearly a bug, and the fix is coming soon. But this is kind of the way to propagate it, and very soon you will be able also to do it. Or if you're using some older versions of Omnitrace, this also works. So now just a few more words about so how do you see this hardware counter? So basically, if you run, let's say you change your Omnitrace ROCm events, in the output at the very bottom of the output of your execution, you will see here the newly created text files. So for example here, and you will see one for each hardware counter. So you will see here for the fetch size and for the value for the memory unit. And you can of course inspect these text files, or what you can do is visualize them in Omnitrace. So as mentioned, if you test this now, the output will be unfortunately empty. So this is actually a screenshot from a previous Omnitrace execution, previous version. But this is in principle how it works. So basically, you can compare here hardware counters to other things and see how they evolve during the execution of your application. Sorry, GPU activity, and here we have ROCtx regions, which George already talked about. So another thing which is quite useful with Omnitrace is sampling. Of course, if you want to reduce the overhead, basically what you need to do is to enable sampling by using this configure variable, or alternatively, instead of Omnitrace run, use Omnitrace sample. And then you can, of course, select the frequency of your sampling as well. And here, on top of all the information that you already collected with Omnitrace, you will see the information about the samples. Very often, this is all the way at the bottom of your trace. So you perhaps need to scroll down a bit. But yeah, so each sample shows the call stack at that exact time of the execution. And you can actually see here the lines which represent the samples. And here, of course, just like the rest of the Perfetto traces, you can zoom in and see better the details of each call stack. And one way to see how to know that some things are sampled is by seeing that this is annotated with S here with the threads. So note this, all this sampling is related to the CPU sampling. So just a few additional features, which unfortunately I will not have time to talk today, but just wanted to mention to you in case you're interested, you can check the documentation. So one of it is that instead of doing this binary rewrite, one can use dynamic runtime instrumentation. Also, there is a user API to control the instrumentation itself. Then there are certain things for other programming languages, like for example, you can profile Cocos if you enable this variable. There is an Omnitrace Python, which supports Python profiling, which is actually only available in this AMD Research ROCm for now, but it will be in the main ROCm software stack soon as well. Omnitrace Casual, which is kind of experimental. And then, as mentioned before, there are a couple of things which currently the latest version of Omnitrace do not work, but will be there very quickly. So one is the hardware counters that I mentioned. Another thing is the full support for the OpenMP. I mean, for both of these, you have seen that these already work with ROCprof v3. But unfortunately, these things are still not in Omnitrace, but they're coming there as well. And another thing is visualization of multiple MPI rank traces, which used to work, but is currently broken due to some things in the Perfetto, I believe. So finally, a summary. So Omnitrace is a powerful tool to understand CPU plus GPU activity on your AMD machines with AMD GPUs. It's an ideal for initial look on how application runs, and it's easy to visualize in Perfetto. On top of ROCprof, it also leverages other tools and combines the data into a comprehensive output. And finally, it helps users analyze the overlaps between CPU and GPU computation and the communication, which is something you do not have with ROCprof, for example. So with that, I will give control back to you, George.
Yes. So we don't have too much time, so I want just to say a few words about Tau on AMD GPUs. Clinical analysis utilities developed by University of Oregon. AMD is not related to this, just we collaborate with them. It's scalable and flexible performance analysis toolkit and has a lot of stuff, automatic instrumentation through PDT, routines, loops, IO memory, phases, etc. This presentation is really minimal because we don't have time. And in Tau, you can compile an application, not compile, but use applications two-way. Or you use the wrappers that Tau provides based on the installation you did with which compiler, etc., if it's MPI or not. Or you have a binary, which you compile it as you want, and use a Tau exec wrapper, and you say use, please, ROCm, a ROC profiler, and profile the ROCm events of this binary. Okay, so this is the easy way, but this provides us some other benefits. And I go quite fast. I'll take the Giacomo here example, okay, and I start here. pprof is an output, is a tool of the Tau. It takes a profiling data and this is your TXT, an ASCII output. And you see 3.0 is a CPU one, and you start seeing the percentage of the time. This is the inclusive, it starts from 100, goes down, okay? This is exclusive time, and number of calls, inclusive, and sub calls, and time per call, etc. So you see the MPI, the heap events, ROCTX events. You see basically all of the events that has application sorted based on the time aspect, how much time it takes percentage. And it's quite easy to do it because you have the binary and you do just that and say, please show me the stuff. And as you continue this TXT that I saw before, you see the thread 1 and 3, you see the copies to devices, etc. This is the communication, and the 0 is the GPU. So you see the actual kernel that's executed, and again, you see how many times the various statistics about time, but you see the main kernels that are used, not the main, the total, all the kernels. Also, there's a paraprof. That paraprof takes a PPK file of that created and creates one PPK file, and you can see here the thread 0 have two MPI processes. So it's basically like two nodes. The two nodes, not physical nodes, but of the Tau nodes. This is the CPU stuff, and what happens on the GPU between them especially. And you can go the mouse over one of these colors and says kernel, what kernel it is. And the metric here is only the time, okay? So you see by time what happens. This is not time, the x-axis. The time you can see here, the variation you can see here from, for example, see minimum, maximum. So you can see the variation of this if it's happen more than one times execution. And you can see if you go from here, there's the windows here, the button, and if you go through the communication metrics, you can see the MPI communication between the different MPI processes. You can sort based on different, whatever the height is, the message volume in bytes, center is 0, and receiver the 1 thread, and various things. So in a big application with a more MPI process, you can see more complicated stuff, I would say. You see the call graph. You see here who call whom, ROCTX, MPI finalized, but this is the, and MPI or reduce is called, and then all the call graph of the application. So maybe you see something who is calling whom, and to get more familiar, especially if you're not the developer of the application. And of course, the color is about what takes most of the time, right? So this one's heap mem set red takes most of the time, for example, on this small tiny example. Then the tracing, you can do tracing, right? Before I show you profiling, I do the tracing, and I say, please merge of the traces. They have some commands to create JSON files. Now, the JSON files from Tau, they are good, because here I have two API processes, and I can merge them and visualize, and I see the CPU, and I see the GPU here. Here is the kernels, here is the communication hosted device, etc. And this is two different API processes. So from Tau, the JSON, I would say it's okay. Tau produces also OTF2 that you can compile, visualize with Vampire, but this is more commercial stuff. And this is a nice example. I don't show you how, I show you because it's a really short talk. There's a way to tell to Tau, please instrument all the loops. Not only the loops, but all the loops. It tells you the numbers are, you see the which file, which lines, the line of the range, and the time, exclusive time is sorted by exclusive time. So you find the hotel loops in the CPU application, this is for CPU, before you port to GPU. This way you can say, I can focus on this loop to try to identify, to see what's going on, for example. And it's really nice. But it's a procedure to do that. I have it in a more extensive talk, not here. Here is more high view. Fortran and OpenAPI offloading, I had the neckbone and the binary, and said, please compile, not compile, instrument the ROCm events, that this is OpenAPI offloading, and like I said, OpenAPI offloading events, and again with statistics about time, etc. This was really nice because actually Omnitrace and Fortran is coming, is not really everything there yet. So we needed something temporarily to cover a bit the time. By that finished also my Tau, and now Luca will continue with the HPC toolkit.
Okay, so even shorter presentation of HPC toolkit. I mean, today we are presenting quite a few tools, and that's why it's every presentation is a little bit short. But just to kind of provide with all the options. So we have seen two first options by AMD. Then George shortly presented Tau, which is not developed by AMD. And then finally, just literally just a few notes about HPC toolkit. So this is yet another not AMD profiler. So this is actually a tool developed at Rice University for the last 20 years. And it's a suite for tracing, profiling, and analyzing parallel programs. So it actually combines the data from static analysis of the program with sampling, and then creates these two types of views. First one is the view for the calling context tree, and the second one is for the time sequence trace view. So something similar to what we see with Perfetto. So the advantages of HPC Toolkit is that it has lower overhead, simple to use, interactive analysis with its HPC viewer. And a very useful feature is that it actually does not require any instrumentation or recompilation, as long as your application is compiled with -G flag. And it supports different things, but most importantly for us, OpenMP. And because, as we said, OpenMP Omnitrace support is still not where we would like it to be. With this, you can actually profile OpenMP, and there is also support for AMD GPUs. So basically, things that you can see with HPC Toolkit, and as you can see, this is kind of a screenshot from one of their presentations, is you can see this type of, you can attribute the cost to the code. So seeing here on the top, the code, and down the calling context tree to see how much time different things took, then different types of statistics, and also here the way to analyze the behavior. Here I have just main parts of the HPC Toolkit. How does it work? Well, it has the HPC run, which is actually for the profiling. It has HPC struct, which is going to analyze the structure of your code. And then you combine those using HPC prof to what they call a database, which can then be visualized by the HPC viewer, which you need to install on your machine. So I think with that, we somehow managed to cover different tools. So as in the previous presentations, the exercises are in this HPC training example repo. So the same one that you used before, that you probably already cloned. If not, you can do it like this here. And then for the two presentations that we had in the beginning, so for the ROCprof, you can check here using this link. So this is you can find there the README for the ROCprof version 3 in our training examples. And for the Omnitrace, you can also find there is Omnitrace folder, so Omnitrace Jacobi, and then you probably want to check for the MI300A if you're using it on our training containers, or there is another one for the 200s in another place just next to it. And there you can check the README and kind of do the exercises similar to what we presented today. And I think with that, I think we conclude this presentation. So I will give control back to George. And basically, we will be here, George and I will stay online. So for any questions, you can ask here or write in the chat, and we'll try to answer.
Thank you, Luca. Thank you, George. You covered a lot of stuff, which was great. They certainly have a lot of things to try out now during the exercises. Okay, so on the schedule, we have 15 more minutes until the break, and then the next presentation at 3:30 Scotland time will be Ian Bogle on Omniperf.
If I can mention about the Tao and Scorpy, so I would say that Scorpy has a nice analysis of trace replay for MPI to find out if some MPI posts are too early or too late between, I don't know, send or receive, this kind of stuff. They have shown also scaling results, but also Tao. I would say Tao does more things. No, Scorpy cannot show the loops. I don't want to make, a VS, because all of them have a reason to exist, I would say. But if you ask me, Tao does more things, but Tao cannot tell you about the MPI if he's posted, I don't know, the send too early or the receive too late, which Scorpy can do it. So it depends on your needs, I would say.
Yeah, I would just add on top of what you already said, George, is that actually, I mean, these two tools, the developers collaborate already for many, many years, and actually there are quite a lot of similarities between them. I would actually say, to be honest, that the biggest difference is that Tao is developed in US and Scorpy in Europe mostly. But of course, there are some small technical differences between the two, and there is a reason for the two of them to exist, but there are quite a lot of similarities, I would say.
Okay. I would get distracted with pings from Teams if I shared my whole screen.
Yeah, and Ian, before we start, would you like to introduce yourself and say something about you?
Sure. So I work with pretty much all the speakers that have gone before me on the same team. We work in HPC applications. Specifically, I work with a lot of centers in the US that are DOE based. And day-to-day work, I mostly work on a code called lamps. So I'm also more familiar with Cocos than I am with OpenMP, but please don't hold that against me.
Thanks, Ian. Yeah, we'll just wait a couple more minutes and then you'll have the floor.
Yeah, sounds good. I will say that this talk does not really talk about Cocos.
Okay, and if you'd like, we're ready for you.
Okay. So this talk is gonna be a quick introduction to Omniperf. And quickly, I want to highlight that this has been a team effort. I'm sure more people than are listed on this slide have contributed to this talk, and if not, at least my knowledge of this tool. So as the other talks have gone over, the profiling landscape, I think you just heard a little bit about Rock Profiler, ROCprof, and Omnitrace. But this talk is going to go over Omniperf, which is a tool that's useful once you've got a decent idea of what your optimization target should be, and you want a little bit more in-depth data to try optimizations. One thing that's really nice about Omniperf is that you can install it yourself in user space. So you can go to the GitHub repo that hosts Omniperf, download a release, build it, and get running with it pretty easily. The instructions are in the documentation here. I usually refer to that when I need to build Omniperf to get some sort of bug fix or something. And we will be talking a little bit about rooflines. So I want to say out front that currently development's still being done on rooflines on MI300A. So on the training container, you will not be able to get rooflines. But I have generated them from MI200s. So if you look at my readmes and in these slides, I will be showing rooflines. Those were generated on MI210s. So if you're not familiar with what a roofline model is, it's a good way of just sort of gauging where your kernels sit in terms of performance limiters on the hardware. So there's a region with this diagonal line that is bounded by HBM or just memory in general. So some memory bandwidth bounds the performance of your kernel. To get better performance, the memory would have to be able to move more data. And if you're under this horizontal line labeled peak flops, that means that you're limited by how quickly the hardware can execute computations. You can't get above those lines because it's physically impossible, and usually being reasonably close to either of those lines is considered good performance. On our hardware, again, this is an MI200 example. We have several pieces of the memory hierarchy. So you'll see multiple memory lines and maybe a few flop lines corresponding to different types in our hardware. And subsequently, there's also a few dots corresponding to each of the pieces of the memory hierarchy so that you can see if you're currently limited by HBM rather than L2 or L1 bandwidth, something like that. So the main piece of this talk is going through some guided exercises. They're listed here. They're supposed to roughly mimic workflows that I've used in my day-to-day work optimizing and profiling applications. So I'll stop here to let everyone get this link that I'm sure has been passed around before because most of our training examples exist on this repo. But all of the examples are at the HPC training examples repo. They are under Omniperf examples. And I'll put the link at the end. The link is on a slide at the end as well, so you'll be able to see it after I'm done with this talk. You can feel free to clone that and get started on your own. I'm going to read through the slides more quickly than anyone should try to get through these exercises, just to give you some highlights, and you'll get the slides afterwards, so you'll have sort of a cheat sheet of things to try with Omniperf and then what you should be able to tell from the output. I also have READMEs on the Omniperf examples subdirectory. They're pretty comprehensive walkthroughs. We did just add MI300A versions, and we'll be looking at sort of moving over to MI300A once rooflines are fully supported. So we used the Omniperf that's included with ROCm 621 to generate the output for these slides. This is available to you on the training container. You can module load omniperf/621, and that'll get you the tool that I used to generate all of the data that you see here. I will say, because it's pretty contended, you will probably see different performance if other people are running at the same time as you are. So if you see different numbers, that's probably why. And also I want to point out that as of ROCm 620, Omniperf is being packaged with ROCm as an officially supported tool. It is undergoing some renaming, but the point here is that we're officially supporting this tool and it'll remain around for the long haul. That said, the Omniperf GitHub, as far as I know, is planning on remaining public, so you're free to build from source and file issues there if you see any. This also means that you won't have to wait for a ROCm release for a bug fix in Omniperf necessarily. So the numbers that are shown in the READMEs and in the slides in certain cases, specifically roofline, were generated using MI210s, but I also have some of my 300A profiling data shown, and I'll be pretty explicit with which accelerator was used in either case. Essentially, if you see a bunch of ASCII output on the slide, that's an MI300A slide, and if you see something that looks like a roofline plot, that's MI210. I also want to really emphasize that the code that we're using to profile and see Omniperf output is not fully optimized. I made sure of that myself, so please do not treat it like production-ready code, because it won't be as performant as it should be. So the exercises are structured roughly in order of how easy things are to change versus performance impact. So we start with something easy like verifying reasonable launch parameters, and then look at some occupancy limiters in shared memory and also register usage. And then the final example has actually got a new spin on it for just this talk, and should be pretty interesting for MI300A profiling. So we do use a simple HIP code for profiling here, but I want to point out that we have verified that Omniperf does work with Fortran and OpenMP codes, and the material in these slides should apply to those codes as well. So you should be able to take the Omniperf commands I give you here and use them on Fortran and OpenMP codes and see the same data and probably draw similar conclusions. I also want to point out that Johanna is working on Fortran and OpenMP examples for common issues with those languages and frameworks. I am well aware that there are probably different issues that are common to Fortran and OpenMP codes that you will not usually deal with in HIP codes. So we're looking to address that. The underlying code that I use is kept very simple, and I also barely mention it in this talk to emphasize how to use Omniperf and what the data Omniperf is telling you should mean to you. So getting actionable insight out of Omniperf data. And yeah, these slides are intended to be sort of a cheat sheet to give you a starting point for using Omniperf, as well as the READMEs, which I keep up to date as I can. So the code that we use is a YAX kernel, which is just a vector matrix vector product. If you would implement it in serial, it would look like this. Obviously, my C++ bias is showing. But A is a 1D array of size n times m, x is an array of m, and y is an array of size n. All the values are 1, just to keep things very simple for the example. And also make certain optimizations a little bit easier to demonstrate in an example setting. So this is a slide that will not apply for MI300A, but in general is a good idea for starting optimizations. Generally, you're not sure which kernels have issues and which ones would be easier optimization targets. So generating a roofline can tell you if your kernel is performing reasonably closely to the hardware limits. The command at the top here with the roof only and kernel names flag should get you both a PDF roofline plot on the system on which you ran this command, and also a PDF that shows which kernel names correspond to which icons in the rooflines. As I said, this is a useful thing to determine which kernels you should look at as optimization targets. But I also want to point out that they're only one perspective of performance. So you could have a kernel that the roofline says is very far away from hardware limiters, but only takes like 0.5% of your entire device runtime. So putting optimization work into such a kernel would save you a very little amount of overall time, even though it might be an easy target. I also want to point out that the generated roofline plots can have overlapping data points because they're just PDFs that we generate once. You can't really fix that in the PDF, but typically they're just hidden. The points are just hidden behind other points, so they're still pretty instructive. A way around this would be using a GUI. I don't really get into that too much, but I'm looking to expand the examples to include GUI examples as well. So all the roof lines that I'm going to show, or actually all the roof lines for every example can be seen on the READMEs. Of course, for MI200, these are currently disabled for MI300A. Support is under active development, and we hope to get that rolled out soon. So this is what a roofline plot would be. Would look like for exercise 1 on MI210. We see that the problem has very poor performance because it is very far away from any of the bandwidth bound lines. And on the right, we see a little zoom in to show what it looks like when a data point gets hidden behind another one. You can sort of barely see the L2 data point peeking out behind the HBM data point there. But they're usually collinear like that, so it should be straightforward to tell where the point is. It's behind one of those two. So getting into more detailed profiling for Omniperf on this problem. In this case, the problem is pretty straightforward. The launch parameters are easy to see. They are in problem, you can see that grid is set to 411 and block is set to 6411. This launches 4 wavefronts to do all the work that we need. And the solution launches just many more wavefronts, thousands of more wavefronts, because we weren't saturating the device at all in the problem. And in this case, it's straightforward to see where the launch parameters are, but if you're using something like OpenMP or another parallelism layer, the framework may decide for you what the launch parameters are. So it's always good to see whether or not the launch parameters of a kernel that's poorly performing are reasonable before you start digging into harder optimization lifts. And Omniperf can easily show this information regardless of what framework you're using. You just need the dispatch ID. And there are other forms of filtering, but those can report aggregate launch parameters. The first example README goes over this more in-depth filtering, but I have a lot to get through in the talk, so I would recommend looking there for more thorough filtering. So the profiling commands that I'll use throughout these exercises remain the same. We just do Omniperf profile, give the workload a name. We pass no roof because the roof line plot generation requires running some micro benchmarks on the system that you're running on. So if you don't include no roof, you'll do some micro benchmarking at the end. And that just takes a little bit of extra time. And in real benchmarks, the profile command can be pretty expensive. So generating roofline data, if you don't really need it, can be just a little bit of extra time that you might want to avoid. It's also recommended that if you can use smaller representative problems than a full benchmark run. So this is what comparisons in Omniperf will look like. I've color-coded this slide to make it easier to parse this first time, but I get rid of the color coding later just because it's I have formatting issues with all these little boxes. Yeah, so the first workload that you specify to that Omniperf analyze command is called the baseline workload, and then the second one will be referred to as the comparative. And if you run Omniperf analyze with these two workload flags like that, you'll see output that interleaves the fields. So you see there's two sum fields. The left is for the problem and the right is for the comparative. And the comparative also shows a % difference from the baseline. And it does this for every metric. So we can see here that there's a pretty good speed up when we launch thousands of more wavefronts than in the problem. And we also see that correspondingly, our total wavefronts launched in the bottom there, 7.1.2, has increased by a large percentage. And there's a corresponding increase in the grid size stat as well, because grid size is just work group size times total wavefronts. I also want to point out, in general, it's difficult to predetermine optimal launch parameters. So if you're looking to get the absolute best performance with just tuning launch parameters, you're probably going to need to experiment a little bit. And then after we make a change, verify that it changed the thing we were after in Omniperf with comparisons, and it's a good idea to take another look at the roof line to see how far we've come. And generally, what we want to do is move up and move to the right. So if possible, that's not strictly speaking always possible, but it should be possible to get a little bit closer to the bandwidth bound line. Ideally, we would be sitting right on it, but that's not always it's not always feasible. So to wrap up this first exercise, the command to check your launch parameters for a kernel is given at the top here. Importantly, dispatch filters by dispatch ID. So in this case, we're getting the second kernel launched. These are global dispatch IDs for the run. So you should double check. And I'll go through how to do this later in a later slide, but you need to see what dispatch ID a kernel of interest has before you can use the dispatch filtering. And then the block argument cuts down the Omniperf analyze output, so it only shows the metrics that you're interested in. Yeah, good launch parameters are essential to a performant GPU kernel, but it can be difficult to track these down sometimes. Your framework might decide for you, but you can use Omniperf to see. And I also want to mention that I omit some Omniperf analyze output that's irrelevant to the talk. I also sort of chop up some of the output so it'll fit on a slide neatly, but you'll probably see a little bit more output if you run these commands yourselves. Okay, So the second exercise goes through looking at shared memory occupancy limits. And this deals with our LDS, which is local data store, which is what we call shared memory. And it's a useful optimization strategy would be to cache some reused data in the local data store. But if you use too much LDS, you can restrict occupancy because this is shared between wavefronts. So if one wavefront requests too much LDS, then other wavefronts can't be scheduled on the same CU. And the problem here is on line 12 in problem.cpp. You can see I very nicely named the variable that fully allocates the LDS, fully allocate LDS, so that one wavefront requests just way too much LDS and keeps other wavefronts from being scheduled. There are two solutions to this because there's two ways to remove the occupancy limit. One of them is to simply just remove the LDS allocation, which does remove the occupancy limiter, but also does not take advantage of caching data in the LDS. The solution in the solution directory reduces the size of the LDS allocation, which also removes the occupancy limit and also manages to be faster than solution no LDS. And because it's faster than solution no LDS, that's the one that I'll be using for Omniperf output in the next slide. And like I said, I use the same profile commands for these examples throughout. Here is the relevant output to see occupancy limit and also whether or not LDS is impacting your occupancy. So we see at the bottom metric 627, insufficient CU LDS. In the problem, it is 57%. And in the solution, we see that it is down to 0. And it's important to note that this statistic, this metric here, does indicate whether or not your occupancy is impacted by a certain hardware resource, but it doesn't necessarily translate directly into occupancy increases. So as we can see, we decreased by around 57% from problem to solution in that insufficient CU LDS stat, but our occupancy in 2.115 increased overall by around like 3%. So we got much less occupancy increase than the reduction to the insufficient CU LDS stat. Yeah, the workgroup manager, which is also known as the SPI, which stands for shader processor input, but I think it's much more helpful to think of it as the workgroup manager, and Omniperf will call it that. These stats will indicate whether a kernel resource or a hardware resource on the CU limits your occupancy. You can get the LDS stat for a single kernel dispatch with this command. Like I said, dispatch ID filtering has some caveats there, but the block is what filters the output, so you only see wavefront occupancy and the insufficient CU LDS. I also want to note a few things about the insufficient resource stats. So these are percentages that that sort of indicate if there is a hardware resource impacting your occupancy, but it doesn't necessarily indicate how severely your occupancy is limited by that hardware resource. As we saw, the big change to insufficient CU LDS resulted in a pretty small change to the overall wavefront occupancy. But I will say, if you see two non-zero fields in that insufficient resource table, which I'll show a little bit, I'll show another one of these later. But if there's two insufficient resource fields that are non-zero, the larger number will indicate which resource is limiting your occupancy more. And also, an important point at the top that I forgot to mention is that occupancy increases don't always correspond to increased performance. And we'll see at one of the reasons that occupancy increases could degrade performance a little bit later. So a similar example, but just sort of a good excuse to look at register usage in Omniperf is this register occupancy limiter that is pretty much solely due to an assert statement and using a very particular set of build flags so that the assert doesn't get optimized out. So in this case, we see a very minor occupancy limit on, I believe, VGPR registers, available VGPR registers. So the different types of registers available on AMD GPUs are called VGPRs, vector general purpose registers. These can hold distinct values for each thread in a wavefront. SGPRs, scalar general purpose registers, which are uniform across a wavefront. If possible, I think using these is preferable just for efficiency's sake. AGPRs, accumulation vector general purpose registers, are special purpose registers for matrix fuse multiply add operations, or they could indicate low cost register spills. Using too many of one of these register types can impact your occupancy and then thus negatively impact performance. And again, same profile commands as the other exercises. And the output is shown here with the command to filter it at the top there. So we see between problem and solution, pretty minor speed up. We also see that the occupancies are very similar, sort of within the margin of machine noise. We do see that the problem was very minorly impacted, so that the insufficient SIMD VGPRs is at 0.06%. So it was non-zero, and we got rid of that. And that was due to the assert. And much more interestingly and more concretely, though, our register usage changed a lot. So we can see that we're using fewer VGPRs in this case. We're using no AGPRs actually, which indicates that the assert may have been causing low-cost register spills, and we're using more SGPRs. So the takeaway here is that functions like assert and even sometimes excessive use of math functions in kernels can degrade performance. It can be difficult to construct a clear example of this anecdotally. This exercise in the past has not shown the occupancy limit because of changing compiler flags. And also, I mean, this occupancy limit is very minor. It just barely manages to impact the insufficient CU VGPRs. But another important point here is that if you see AGPR usage when you're not using MFMAs, that can indicate degraded performance, specifically that you're spilling registers to AGPRs due to running out of VGPRs. And this command at the bottom here will show you all of the workgroup manager insufficient resource stats, but it will also show you more than just insufficient resource fields, but it's a good first blush which of these stats is limiting my occupancy the most command for Omniperf analyze. Did I hear a question? I thought I may have heard someone. All right, moving on. So this is the final example that I'll go through today. So as probably everyone here is aware, data access patterns are important to performance. The way threads access memory impacts how memory accesses go through the cache hierarchy. And if you ask for data in a certain way, the cache hierarchy will be used a lot less efficiently than if you ask for it in a different way. These access patterns can be difficult to spot in your code because they're valid methods of indexing data, and the only indication will be the performance is worse than it should be, but determining what it should be can sometimes not be straightforward. And specifically, the setup for this example may be less applicable to OpenMP codes, But these commands are still useful because they can tell you if your cache access patterns are currently adversarial to the caches, just to get an idea of how your data accesses are hitting our L1 and L2. So in case you're not aware of what a strided data access pattern is, essentially it's when threads access data elements that are very far away from the data elements that other threads are accessing. This is adversarial to the caches, and much better is to increase the locality of data accesses with respect to threads nearby. So we see that thread 0 is accessing data that's right next to the data that thread 1's accessing, and that goes the whole way to thread 63. I want to point out that the change that was made here is very simple because all of the data underlying this problem is 1. We just had to change the way we were indexing the matrix A because it was functionally the same as changing the way we were allocating it. So in general, this is going to be much more difficult in real codes that aren't very contrived examples. And reconceptualizing how your data is structured can also be pretty difficult, and you have to change how it's being indexed everywhere in your code. I also want to point out a little bit in some foreshadowing that highly contended atomics on the same global memory address is not a good thing to do. This code example does that, and production codes should avoid this. So let's look at the L1 hit rate here, which is a ridiculous percentage higher in solution than problem. So typically, it's difficult to say what a good L1 cache hit rate is, but 0% is pretty bad, and 75% is much better. And this should result in some speed up, even though our L2 hit rate goes from around 93 to less than 1%, because we're able to hit a lot more in L1, which is a lot closer and should be a lot more efficient than getting everything out of the L2. But we see at the top there that we have around a 30% slowdown, which is counterintuitive because our cache pattern looks to be better. So let's real quick check on atomic latency, because as I mentioned, this code does something bad with atomics. And yeah, so we see that the code, the solution for some reason is it just has more contended atomics. But also at this problem size, the kernel's bound by our atomics, most likely, because we saw that our cache accesses were much more efficient. So the slowdown has to be due to the kernel being limited by atomics rather than our cache bandwidth. So my current theory about why this happens is that because solution uses the caches a lot better, rather than having to go out to the L2 for everything, this greatly reduces our memory latency and ironically increases the contention and pressure of atomics because all the threads hit the atomics more or less at the same time, whereas in problem they had to wait for data to come back and probably got through the atomics with a little less contention. This, coupled with my bad atomic heavy reduction strategy, means that atomics are a limiter, not cache. I also want to point out that this is the midpoint of the exercise. I want to explicitly state that the lesson here is not use suboptimal cache access patterns. We'll get to the true lesson, but this is a little bit of sort of a diversion here to illustrate an optimization pitfall. So since we're limited by atomic latency or atomic bandwidth, it makes sense to try to move away from having every thread do an unsafe atomic add on the same global memory location and try to use a shuffle reduction to reduce the atomic contention. A shuffle reduction is implemented in the code in the mi300a_problem and _solution directories in the repo. So you can see how that shuffle reduction's implemented there. Essentially, it should cut down the atomics by a factor of 64, just because we're having only one thread do an atomic add instead of all of them in the wavefront. And again, Optimizations of this type likely have much more development overhead and real codes. You have to change how the data structure is indexed everywhere, and also these reduction strategies can be costly to refactor. So after we rework the reduction strategy, we see that we still have around a 30% slowdown, even though we did get the atomic latency a little bit better. So it seems that even though solution uses the caches better, we're still bound by atomic latency because the atomic reduction is bottlenecking our code no matter how few atomics we use. And the solution is always going to be a bit more contended than the problem. So the atomic reduction will always take longer in the solution than the problem. But and this is part of the intended lesson behind this exercise. As our problem size grows, our cache access and data movement will get more expensive. And for larger problem sizes, our cache access and data movement should be the bottleneck. And the true lesson of the exercise is profile a representative problem size, because you can, if you profile a smaller problem like we did just before this, you can get misleading optimization ideas, such as we should reduce our atomic contention, when if you run a larger problem size, you might see different performance in your profile. So we'll run these commands at the bottom, which are slightly different because the executables MI300A problem and solution have a runtime argument. So if you pass 15, you'll increase the problem size, and we will see output that looks like this. So we see about a 12x speed up between problem and solution when we increase the problem size. And actually, this is even true if we revert to the old worse atomic reduction. That isn't a shuffle reduction, but I don't show data for that. You can try that on your own if you're interested in seeing it. But the hit rate we see much better. We also see that our L2 bandwidth increases a lot, even though our L2 hit rate also decreases. But finally, we see that switching to a better cache access pattern gives us the speed up that we were expecting from the start. So use good cache access patterns. Also, make sure that the problem size that you're profiling is representative for your use case. Otherwise, you might spend time optimizing things that aren't your production bottlenecks. So if you're just interested in getting some data about the L1 and L2 cache accesses, you can use block 16.1 and 17.1 to get the top level statistics for those cache systems. Generally, ensuring better data locality will give you better performance. And it has been my experience, though I assume that this is not a general rule, but if you start hitting in the L1 cache, you usually see your L2 hit rate degrade a little bit. In this case, it was a lot, but L1 increases at the expense of L2 decreases is usually an acceptable trade-off. If you increase your cache efficiency but are running a small problem, you might want to check atomic latency if you're using atomic reductions, just to see if maybe the problem's too small and you're getting bottlenecked by atomic latency or bandwidth. And again, you can tell I'm a little bit paranoid about these sorts of optimizations, because in a real code, optimizations of this type likely have much more development overhead. It's a non-trivial change. So that is the final exercise I'm going to be going through. I have a few tips and tricks that haven't made their way into official example material yet, specifically for long-running benchmarks. So like I said, production codes usually take a long time to run, and Omniperf requires running your code quite a few times to gather a full set of performance counters. So you can filter by the kernel name and also metrics that you want to collect during the Omniperf profile run. And this should cut down on profiling time. The syntax for cutting down for just filtering certain kernel names is right there, the -k flag with kernel name and double quotes, and you can filter several kernel names by just separating them by a space. And also, if you don't surround your kernel name in double quotes, spaces are the delimiter. So just to be safe, I would recommend putting them in double quotes because you don't want to search several kernels that are actually just one kernel name. And also, Omniperf applies the wildcard automatically. So this will get unique substrings. It'll match, if you just get a piece of your kernel name, it'll match unique substrings so you can get all of the matches. It's useful for Coco's code. I'm not quite sure about OpenMP. But I also want to note that as of right now, Omniperf Analyze also has a K flag. The K flag for Analyze does not take a kernel name. It takes an index, and that is the index of the most expensive kernels ranked by kernel runtime on the device. So if you do Omniperf Analyze -K0, you get the most expensive kernel run with respect to aggregate kernel runtime on your device. You can see the index to kernel name mapping on the table that Omniperf outputs, but if your kernel names are too long, you can also generate that data with list stats and it won't truncate those kernel names. Also, if you know the metrics you're interested in ahead of time, which probably is more of a power user sort of thing to do, but you can cut down on how many ROCprof runs are required by specifying the block at profile time. These do use acronyms that are a little bit archaic, I would say, but something like SQC standing for Shader Sequencer Controller. So mappings of these acronyms to what they mean in terms of metrics can be found in the some of them can be found in the Omniperf documentation, but we're always striving to make these interfaces a little bit less confusing to work with. Omniperf profile --help will show you all of the blocks that you can collect. And then again, the performance model can help you decode what that means in terms of the metrics you'll be able to see. So I also wanted to mention, because George was talking about ROCprof v3 being the one to use in ROCm 6.2.1. So Omniperf currently doesn't support ROCprof v3, but it is coming. And ROCprof is recommended until then and should work for you on the training container. I also want to shout out Johanna again. She's developing Fortran and OpenMP examples. These are currently located in Omniperf-OpenMP/Fortran. There's one fully finished example, but more are planned and are under active development. I also want to say, if you have success stories with any of our profiling tools, feel free to reach out to us, because our team works pretty closely with the profiler teams, and we really like to relay the impact of their work directly to them. And also, it's pretty hard to come up with good examples that are representative of real use cases if we don't hear from customers that have real use cases. So your experiences could help improve the quality of our training material. I also want to point out that the HPC training examples repo will be monitored, so you can feel free to create an issue if you find something that's wrong or broken. And also feel free to suggest improvements you feel would improve our training materials. All right, so I think that's all the material I have to cover. I am going to leave it on this slide so you guys can have the links. I'm sure that they're being distributed in the Mattermost as well. But yeah, I'll let you guys work on the examples and be around for questions.
Thanks, Ian. That was a great presentation. We've got half an hour reserved for exercises, and then at 4:45 Edinburgh time, Bob will wrap it up and show also some additional training resources that we have available. Okay, we are 5 minutes away from the final presentation by Bob. Bob, if you'd like, if you're on, please try and share your slides. Thank you, perfect. I'm just gonna take a second to thank all the participants and speakers for this event. It's been really a great success. We're very happy. And your level of involvement, it's been great. We're very grateful for all your questions and comments. And yeah, I'm just gonna hand it to Bob for the final presentation and remarks. And thanks again.
Thank you, Giacomo. So we're just going to wrap up with some summary of other materials you can look for that can help you as you dig deeper into the different topics that we've talked about or other topics that we haven't covered. Here's a short list of them. We've got different blog type posts that you can look at. We'll give a list of some of those, videos from other events, books, and we'll also look at the kinds of things we do for training. So first of all, we typically have several styles of training, and each of them are customized for the different site. Our big goal is to try to get a good number of people into these training events or hackathons. Training events, we generally do those virtual. Hackathons, we usually get a couple staff members there and maybe some local site support staff. So system administration, introduction, we're finding increasingly that, how to install the software for the best results is a very difficult task these days. There's just too many software packages. And Giacomo and I have been struggling to try to get them all installed and working. And we're recording our progress and getting help from experts in different applications. Training workshop, that's basically what we did here. And we can go up to 90 participants. We do like to have more than, 4 or 5. We really like to get somewhere around 30 to 90 participants in a workshop. And we can launch more than one node with the training container if the workloads start getting pretty heavy. Hackathon, we usually do around 3 full days on site and about 8 teams, 3 to 4 people, and usually a pre-hackathon. So if down the road that any of these look interesting, or special topics training, we do those sort of as one-off events at different sites such as Oak Ridge and other sites that have a lot of users. AMD lab notes and ROCm blogs. A lot of this is moving over to ROCm blogs, but there's a lot of different write-ups on different topics. Some of these write-ups have already been mentioned in the presentations over the last few days, but that's a good resource to go find more material on things like, maybe we didn't cover AMD matrix cores here and you have some interest in that, then that might be a good resource, or just more in depth on the ROCm installation. So there's a lot of nice articles and these are put out about monthly cadence. That draws from a lot of our experts within our team. It is focused on generally high performance computing and some of the AI apps that are used in HPC centers. So we have videos from this event. So you do really suggest you go back and look at some of these and for the topics that you're interested in. Often seeing it again, you can catch some of the things you missed the first time. And it may be good, after you start working with, let's say, OpenMP, you go back and review some of the presentations on that. We also have videos from other events that we've done. So the most recent one is we did an event for HLRS Stuttgart in April, and they've posted the slides and the recordings for all the different talks that were done over that 4-day event. And you may find more detail on a particular topic that you're interested in. And then, as I said, there's often special presentations at some of the sites that we work with. So Oak Ridge is one of them, and you can see there's a long list. You can search for all the talks done at Oak Ridge, and some of those might be interesting to keep up on the latest of what's happening. A little bit older one is one we did in Stockholm. And so there's a lot of presentations from that. From that one, it's November 2023, so it's getting a little bit older. And unfortunately, things do keep moving forward, so more recent ones are usually better ones to look at. We improve our topics, in our presentation, but also the hardware changes. So November 2023, there would have been a little mention of MI300A. Pawsey did a special session just on profilers. And so we did fairly long presentations there. Then for software documentation, of course, one of the best sites to go to is the ROCgdb site. That's being rapidly improved and updated. AMD developer site, so they have a whole host of different materials. They do have some videos, but they're getting even older. But you might look at the developer site and see what kind of different opportunities you might have there. There is a book on HIP programming, and soon we're going to have a HIP certification class, so that people can get a certification and testing on their proficiency with HIP. Some of the sites actually, they've generated really excellent materials, from our initial briefings and information on the hardware and the software. So you might look at sites like Oak Ridge, the Crusher Quick Start Guide, the Frontier User Guide. We'll probably see similar from LCAP and other sites. Also, and last, we've mentioned a few books. So the Accelerated Computing with HIP, that's a good resource, and that gives a thorough background on the HIP programming language. We got a recommendation from our OpenMP gurus that this new OpenMP programming book, it's hard to find books that are current in some of these topics. And of course, if you're 6-7 years old in OpenMP, you may not even have much on GPU programming. So this one actually addresses GPU programming with OpenMP. And then, of course, my book, which is sort of a general reference covering wide array of topics that are important to parallel and high performance computing. And that often is a good reference if you just want to get a good solid foundation. And some university classes have picked that up as their textbook. And I think that's it. Okay. And so I want to turn this over to first Giacomo to close out, and then to Juan as our host to close out as well. Giacomo?
Thanks, Bob. Yeah, sorry, I'm trying to turn on my video. Okay, thank you very much, Bob, and thanks a lot for making it for this last couple of days. We really appreciate it. Yeah, so just to wrap it up, once again, thanks to everyone in attendance. I think the event went very well, and let me just make a note that the AAC node will stay up until October 10th, so you can still keep using it, and if anything comes up, just shoot us an email and we'll get back to you ASAP. Yeah, Juan, I'm gonna hand it over to you. Thank you for organizing this and making sure that everything runs smoothly. We really appreciate your involvement and your assistance with everything.
Thanks, Giacomo. Well, thank you for delivering this course, mentioning the mattermost, but no, I think it's also worth mentioning that the quality of the presentations material is really good. So thanks. Also, thanks to the attendees. Two brief comments. The first one is we will send maybe maybe because now it's Friday afternoon UK time is not right. But well, I will post the feedback form. It's pretty. I mean, could be you can spend more time with the feedback form, but there is only one a mandatory question that just a click. So please, if you can reply to that feedback form, that would be very helpful for us. Also, as you may know, these courses are free, but we need to report like a good number of feedback responses. So please fill in the feedback form. And the second thing is we also provided access to ARCHER2, and I guess that because ARCHER2 has a different model of GPUs, not all of the exercises will work, but you can still play around and see the differences and see how things behave. And the Mattermost channel will remain open, so I will try to keep an eye. So any questions, please let me know. Well, yeah, thanks everyone. Have a nice weekend ahead.
Thank you, Juan. Thanks, everybody.